Okay, hi everyone. This is our last lesson in the limits unit, and we're talking about two theorems, the squeeze theorem and the intermediate value or IVT theorem. The squeeze theorem says that if you have three functions, so in this picture we have a function f, a function g, and a function h. And as you can see in the picture, the g function is trapped in between the f function and the h function. So in other words, the y values of g are always, not always, but let's say for an interval, here's the x value that we're interested in, x is equal to a. So around this x value of interest, right, the g function is trapped in between the f and the h. So in an inequality statement, we could say g of x is greater than or equal to f of x. So it's greater than or equal to f of x, and it's less than or equal to h of x for all x in an open interval containing a, except possibly at a itself. So that means for some space around this arrow number a, for some x interval, we've got this situation. That's condition number one. And condition number two is if we can say that the limit of these two outer functions in the inequality, so we're talking about h and we're talking about f, right? The two functions that are on the outside of the inequality, if those two limits at this arrow number approach are not approach but are equal to L. If the two limits on the outer two functions are L, then the inner limit at that arrow number, which is the limit of g of x as x approaches a, must also be L. So just in less formal terms, what we're saying is that sometimes, say we have this g function and none of our other methods of finding the limit for g of x as x approaches a are working, numerical a table or a graph or algebra, we're not able to figure it out. Well, one more sort of tool in our toolkit is this squeeze theorem. That says that if we can find two other functions for which we know the limit is the same number L, any number L, if we can find two other functions that have a limit of L, and if this g function is trapped between those two functions around x is equal to a, then it's as if those two outer functions are squeezing the g function together, right? So as you approaching the arrow number, the g function has nowhere to go. If the two outer functions are approaching a limit of L, then g is kind of squeezed or pinched or sandwiched or trapped to that same limit, okay? So that's the theory. Let's take a look at a couple of examples. So I want to remind you of a special limit that we talked about, which was it a special limit? No, I take that back. It was an oscillating limit, right, that we talked about, which was the sine of 1 over x. So this graph is sine of 1 over x, and we talked about how as x goes to 0, this function just oscillates. Oscillates means goes up and down, jumping up and down faster and faster, right, as we get to 0. And therefore, it doesn't settle down to any number, and the limit here is a dne. That's one way, right, in which a limit can fail to exist. And sine of 1 over x at x is equal to 0 is an example of that. Well, if you take this sine of 1 over x function and you multiply it by x, so over here I've drawn the function y is equal to x times sine of 1 over x. Notice that the graph looks very different already, and if you were to zoom in here, in fact, this limit, the limit of this x sine of 1 over x as x goes to 0, is now equal to 0. You can kind of see that, not really on the graph, but the point is that by multiplying this this oscillating sine 1 over x function by x, it changes a lot, and the limit at x is equal to 0 now exists. And we can prove this using the squeeze theorem. And the way we would do it is to start with the first step to say that sine of 1 over x is always between 1 and negative 1. Sine of anything is always between 1 and negative 1. Now, step 2 would be, see, we're setting this up to have those three functions, like the theorem said. We have a f and a g and an h, right? So now we're going to take these outer two functions. Actually, we're going to take the whole thing and multiply by x. And why am I doing that? Because here, I know the function I'm trying to talk about is x sine of 1 over x, right? And so if I multiply the entire inequality by x, I'm allowed to do that. Now I have this function that I'm interested in, this guy, right, sitting in here. And now I can apply the squeeze theorem, and I can say that since I know that the limit of negative x as x goes to 0 is 0 by direct substitution, and I know that the limit of x, this outer function on the right, also as x goes to 0 is 0. Notice the arrow number is 0 for all the limit statements I'm going to make. Since those two outer functions are going to 0 as x approaches 0, this inside function, x sine 1 over x, also must go to 0, right, by the squeeze theorem. Notice how I'm writing this out. You have to kind of say the justification in this way when you use the squeeze theorem, right? So to recap, there are two conditions for the squeeze theorem. The first is that we have a function which is trapped between two other functions. That I showed that in step 2. And the second is I have to show that the outer two functions at the arrow number, whatever arrow number I'm interested in this problem I was trying to show you that this function goes to 0 at x is equal to 0. So my arrow number was 0. So at that specific arrow number, I have to show that the two outer functions go to 0. And then I can invoke the squeeze theorem and say, therefore, I know that the inner function also goes to 0. This might seem a little obscure, and I don't blame you for thinking that. Let me just say it's part of the AP curriculum. Is it one of the most important things in the course? Absolutely not, but we are covering it because it is part of the AP test. Okay, so let me give you another example. Here we have the problem in example 2. It says if 2x is less than or equal to g of x is less than or equal to x to the fourth minus x squared plus 2 for all x, find this limit, right? So when you see this kind of setup, your mind should just be, lights should be going off, flashing red lights that say squeeze theorem, right? Because we're dealing with a limit and you've got three functions and they're set up in this nice little inequality. So this is just crying out for the squeeze theorem. So let's kind of use the squeeze theorem here. So here they've already given you the inequality. Now all you need to do is show that the outer and inner the two outer functions go to the same limit. Use the same arrow number and check where the two outer functions go to, and you're going to see just by direct substitution that in this case both of them go to 2, right? So you can say since that is true, and already we've got the inequality in the question, so you don't even have to repeat that. By the squeeze theorem, the inner function, which is the g of x function, is kind of trapped and has to go toward the same limit of 2. Okay, so that's how we answer this squeeze theorem type of question. Okay, second obscure theorem for the day is the intermediate value theorem, or the IVT. Intermediate, the word means in between, right? That's all that it means. So the theorem says that if f of x is continuous, so for the intermediate value theorem, the function has to be continuous on some closed interval, right? A, B. These are x values, an x stretch of the axis, x-axis. If f of x is continuous on the closed interval a, b, and if n is a number, any number in between or intermediate, in between and intermediate mean the same thing. N is any number in between f of a and f of b, then there must be at least one x value c in this interval a, b the open interval AB such that f of c is equal to n, right? So that, I'm sure, was confusing when we stated that way, but let me break this down to a very simple real-world example. If you weighed 50 pounds when you were 10 years old, and now you weigh 125 pounds when you are 17 years old, let's answer the following questions and let's justify our answer or provide a counterexample. Remember the whole time that your weight is a continuous function of time, right? So I'm gonna actually be using the IVT, and I'm reminding you here that I have noticed that my weight is continuous. Every theorem in math has some conditions, and if those conditions are met, then you can use the theorem. The IVT, the conditions are, first of all, that we need a continuous function. So your weight is a continuous function. Okay, now the question is, first question is, did you absolutely positively weigh 90 pounds at some time between ages 10 and 17? Well, if you look at the way this question is set up, you can think of 10 years to 17 years as a stretch of time, right? This is a stretch of X values, 10 to 17, right? And we're saying you weighed 50 pounds, right? So your Y is up at 50 when you are 10 years old, and you're up at 125 when you're 17 years old. So did you absolutely positively weigh 90 pounds at some time between ages 10 and 17? Yes, you must have, because there's no way for your weight to have gone from 50 to 25 without crossing 90, which is somewhere here, at least one time, right? A Y value of 90. So that is all the intermediate value theorem is saying. And to justify that in our first answer, we can just say yes, because the simple reason is that the weight is continuous. And the other reason, that's one reason. And the second condition is that 90 is between your weight at age 10 and your weight at age 17, right? So that's all that the intermediate value theorem is saying, that you are hitting every weight in between 50 and 125. So the function is hitting every value. If you think of this as A and B, this 50 is f of A and this 125 is f of B. So your function is hitting every single Y value between 50 and 125 at least once, while your X goes from 10 to 17. Okay, next question. Did you absolutely positively weigh 135 pounds at some time between ages 10 to 17? And the answer here, pause the video and think about it, would be no. And the reason is because 135 is greater than f of b, or 125, right? So clearly I just drew this picture for you here. It shows that I could have gone from 50 to 125 without hitting 135. Okay, the next question says, did you absolutely positively not weigh 135 pounds at some time between ages 10 and 17, right? And the answer here would be no. It could be that my weight did something like go from 50 to 125 in a way where, I went through a little chubby phase when I was 13 years old, maybe, and my weight went up to 135 and then I came back down to 125, right? So we're not sure. There's a counterexample right here that I've provided to show that we cannot be sure that we didn't get out of the range. All the intermediate value theorem is saying is that we must hit every number in the range at least once. That's all we're saying. Okay. Did you absolutely positively weigh 90 pounds at some time between ages 10 and 15? Now, here, notice my initial statement is that at age 10, I was at 50, right? The question says, and age 17, I was at 125, right? So somewhere in part A, we said that somewhere along ages 10 to 17, I must have hit 90, right? But in this part D, if you want to call these A, B, C, D, in part D, we're saying, did you absolutely positively weigh 90 at some time between age 10 and 15, right? And that we cannot be sure. Not necessarily, right? You might have hit 90, right here when you were 14, but you also might have hit 90 when you were 16. We don't know. We don't know what exactly happened. All we know is that you hit 90 at some point, right? Okay, so this is what the intermediate value theorem is saying that if you have a continuous function like that weight, and you're on a closed interval like 10 to 17 for our age, and if n is any number like the 90 in between the 50 pounds and the 125 pounds, right? Then there's at least one x value, one age here in our example where your weight must have been equal to 90, right? That's what we understand from that theorem. There's another way in which the intermediate value questions often appear, which is to do with x-intercepts. And about x-intercepts, what we need to realize is that for an x-intercept, y is equal to 0, right? So f of an x-intercept is equal to 0, okay? So when you have a function here, this is a polynomial, and you're looking for an x-intercept, this question says, does this polynomial have an x-intercept between x is equal to 1 and x is equal to 2? And of course, you guys would just reach for the calculator maybe and graph that and figure that out. But what if you didn't have a calculator? Well, then we could use the intermediate value theorem, and we could say this is a continuous function. Remember, that's our first condition for the intermediate value theorem. Second condition, we might want to be more complete and say f of x is continuous everywhere, right? Because it's a polynomial. Second thing we want to do is take this is our a-b interval. So let's find f of a and f of b. So 4 times 1 minus 6 times 1 plus 3 minus 2. Left to right, negative 2 plus 3 is positive 1 minus 2. That's negative 1. And let's find f of 2. F of 2 is 4 times 8 minus 6 times 4 plus 3 times 2 minus 2. 32 minus 24 plus 6 minus 2. Left to right, negative 8 plus 6. That's positive 8 plus 6, that's 14. 14 minus 2 is 12, okay? So now I can see that f of x changed sign on this interval, right? F of 1 was negative 1 and f of 2 was 12. If your function is changing sign, then it must have gone through a y value, which is 0, right? On the x-axis, y is equal to 0. So this is another example of the intermediate value theorem. We can say it this way. F of x is continuous. F of 1 is negative 1. F of 2 is 12. And we could say since 0, right, the y value at the of an x-intercept is between f of 1 and f of 2, right? By IVT, there must be at least one x-intercept on this interval 1, 2, right? And just graphically what we're saying is, we know we're talking about some function. We don't know what it looks like, but we know that f of 1 was negative 1 down here, right? And f of 2 is up here at 12. So since the function is continuous, there must be at least one place where I hit the x-axis, right? On this x-axis, y is equal to 0, right? So it's whatever the number is, comma 0. That must have happened at least once. It might have happened more than once, right? But because the function is continuous, we can make that statement using the intermediate value theorem. Okay, so this is our last couple of multiple choice questions. So I'll pause the video and read number 5 here. So for number 5, we're being asked which of these statements we need to pick if we are to conclude or to make the conclusion that there is some value x equals c in the interval negative 1 to 1 such that f of c is equal to 3, right? So we need two conditions for the IVT. The first one is continuity, and the second one is that the number, the y value we're looking for, right, is between the y values at the two ends of the interval, right? So we've been given this condition already in the question. So the other thing we're going to need is that f is continuous. So it would be answer choice C. And if you're wondering why A and B are not sufficient reasons, I'm just going to draw a quick picture here to kind of disprove A and B. You could have a function that looked like this, right? At -1, f of -1 could be down here, and then f of 1 could be, somewhere up here. 3 is somewhere in between those two values, right? But if the function did something like this, actually, let me change that a little bit. If the function did something like this, right, then it meets all what the question said. It meets the fact that 3 is in between f of -1 and f of 1. It also meets the fact that we're on the closed interval -1 to 1. However, because there's this break here, right, we never hit the y value of 3. There's no x value between -1 and 1 where we hit a y value of 3. And that's why for intermediate value theorem to work, continuity is an essential condition. Okay, last problem is about the same thing, IVT. It says let f be a function of x, which of the following statements, if true, would guarantee that f of x has an x-intercept in the interval from -6 to 5, right? So it's the same idea that if I'm on this interval from -6 to 5, if my function changes sign, if my f of -6 is negative and f of 5 is positive, then and you can see in each of these choices, that's the first thing we're going to check, is you want to change in sign between the y value at the two ends. If it's happening that way, then if the function is continuous, there must be some place where you crossed the x-axis, right? There might be more than one place, but there's at least one. So I think in this case, we are looking for continuity, and we're looking for a change in sign of the y values at the ends. So the one that I would pick here is answer choice C. That would be the right answer. Taking a look at E is actually very close to C. The only difference is the interval is an open interval, right? So I just want to draw a quick picture to show you that we really do need a closed interval to have the IVT work for us, because if you have an open interval, then you could have a situation like this. So I'm on this open interval, f of -6 is -1, okay, and then f of 5 is 3, so I'm here, right? So all that's great, but if it is continuous just on the open interval, then the function could be in fact just something like that, right? So in other words, I could have that function right there that I drew is continuous on the open interval from -6 to 5. It meets the condition that f of -6 is -1 and f of 5 is 3, right? However, notice that I never crossed the x-axis, so there was no x-intercept. So we have to be careful for IVT. The interval has to be a closed interval. So take a couple minutes to write down the squeeze theorem and the IVT in your own words. And yeah, I hope that obscure as they are, these two theorems kind of make sense. They're really not that hard in terms of what they're saying, but they're just a little bit abstract. But I hope that you understood, and I'll talk to you in the next video. Thank you, guys.